Be reviewing. On Wednesday, you're going to take a quiz over Chapter 2. So that goes all the way back to when you started graphing parabolas. So you need to go back and review those different forms and how to graph. And then also how to write equations of parabolas. And then on Thursday, we'll review. And on Friday, we'll take the test. But it goes back all the way to Chapter 1 and Chapter 2. So after today, you have all the information you need for your test on Friday. You should start studying a little bit each night, right? Read through your notes, review a section or two, retry some problems that are in your notes. Those things would be good to do. Today, we're going to do quadratic models given 3 points. But what's important to note is in your 3 points, you have no vertex. And no x-intercepts. Because if I had the vertex, I would use vertex form. If I had the intercepts, both x-intercepts, I would use intercept form like we did on Friday. So this is like, I know 3 points on a parabola, but I don't know if they are the vertex or if they are the x-intercepts. Okay, they're just 3 random points. Okay, so we're going to put it in context of a word problem here. Okay. The table below shows the estimated profits, which is Y, in dollars for a concert. So here's our profit, nice little chunk of change right there, when the charge is X dollars per ticket. Okay, so we're going to charge different amounts per ticket. Now, one thing to note about like something like this where you're just given a table of values is nowhere in this statement up here does it tell me to like write an equation for a parabola. I don't have a picture of it that it's a parabola. So one thing that you kind of want to be aware of is you might have to look at, like if you're given a table of values, what type of model should I write? If it looks like a parabola, then I should use a quadratic model. But if it would look like a line, I wouldn't want to write a quadratic model. I would want to write a linear model. So I would use like y equals mx plus b. Okay. So there's a couple of different ways that you can go about doing this. I think everybody, because we have kind of big numbers, you probably want a calculator today. If you need a calculator, come grab one. Tell someone in your group if they're going up to get you one if you need it. So notice my directions here at the bottom say write and evaluate a function to determine what the charge per ticket should be to maximize the profit. But function, right now, we don't know if it's linear or quadratic. Like which one should we be writing? So I'll kind of talk about different things that you can do. Here's the most common thing that mathematicians are going to do. They're going to look at the differences in the x's and the y's and whether or not you have constant slopes. Okay. So notice your ticket price. How are we changing the ticket price each time? It's going up by 3s. Okay. So that means like in terms of slope, I can really look now at the change in the y's and see if it's changing by the same amount each time. Okay. Obviously, we're going to be writing a quadratic model, so you can guess this is not linear, but we're kind of like thinking like, what if we saw this on our own? How would we determine? Okay. So now let's look at the differences in the y's. So 6,500 minus 2,600, that's what, 3,900? Somebody's got to check my math for me. You all have calculators. I'm doing it in my head. 6,500 minus 2,600? 3,900? 8,600 minus 6,500, let's see, is that 2,100? 8,900 minus 8,600, that's 300. I mean, obviously, can you see it is not linear? Okay. So these things are what we call first differences. first differences, here I'll write it out, differences. If the first differences are the same and you're like changing the same for your x's, then that means you have constant slope and it would be linear. But since the first differences are not the same, it's not linear. Now, what's really cool as we study quadratics and then like even higher level polynomials like cubics and quartics, mathematicians can kind of decide if one of those polynomials might be a good model by looking at the next set of differences. So we have the first differences. Now we're going to look at second differences. Okay, for second differences, you take your first differences and look at those. So like 2100 minus 3900, that's what? Negative 1800. No? 300 minus 2100, that's negative 1800. And if I wanted to keep going, I could look right here like, okay, so this one, 7,400 minus 89, that's negative 15. So negative 1,500 minus 300 is another negative 1,800. So we're seeing a pattern there, right? Since the second differences are the same, it means it's quadratic. Okay. Now, let's say the second differences weren't the same, but you had this set of data and you were tasked with like writing the model so that we could predict something in the real world. Then you might, if you were a modeler, you might choose to check the third differences. Because if the third differences are the same, then you could use a cubic polynomial to model that data. I'll also put in like a little like asterisk here. If this was real data, you know, like if we were like surveying something in the real world, like people getting sick or something like that, the numbers probably aren't going to be perfect, right? Like negative 1,800 every time. Because we're working with money here, it makes sense. Okay? But even if in the real world your numbers weren't exactly alike, if you notice that the differences, like the second differences were pretty close, then you might say, well, it's not a perfect parabola, it might be a good model for my data. Okay, so that's one way for you to check what type of model you should be using, whether it's linear or quadratic. Take a moment, think to yourself, linear or quadratic, given a table of values. Can you think of another way that you might have been able to check if you should use a linear or a quadratic model besides this first and second differences? Delaney?
Could you put 3 over 3,900? Like, could you calculate if they were the same?
Oh, like 3,900 divided by 3 and 2,100 divided by 3. Yeah, because then you're checking the slopes.
Yeah.
But I know that if I take different numbers divided by 3, they're not going to be the same thing. So then I know the slope isn't equal. So yeah, that's kind of like checking first differences. Now, if the change in the x's hadn't been constant, I probably would have done that, right? Like actually check the actual slope. But since their change in x's was the same, I could just look at the numbers, 3,900, 2,100. Anybody else got any other ideas? How might you else be able to tell if the data looks linear or quadratic? Keyword looks. What's that? Oh, okay, look at your table. 26, 65, 86, 89. It's going up. And then 74, 41. It's going down. Does a line go up and then down? No. So if you think about it visually, whether you're plotting the points or you're just thinking about if you were plotting the points, if the data is not appearing like a line would be constantly rising or a line would be constantly decreasing, right? If the data is not doing that, if it turns around at some point, you also kind of know you should use a quadratic model, right? At least in this chapter. Now, note, there's lots of models to be made. We're just learning about linear and quadratics right now, so those are your only two options. Okay, so that's kind of like a long story about linear versus quadratic, but if you're going to go on into like a mathematical field and you're going to be modeling things, you need to know more about what to do with data, okay, and how to decide what you want to do. Okay, so we want it to be quadratic, right? Now we might look at this table and see if we know anything like x-intercepts. In a table of values, if you had a point that was an x-intercept, you would know its y value would have to be equal to 0 on the x-axis. But since I don't have any y's that are 0, I don't have any x-intercepts. I might look for my vertex. And if you think back to what Mo described, how it was going up and then it came down, we might look at 11 and 8900 and think maybe that's the vertex because that's the max point, right? But then when you look off to the two sides of it, an equal distance away on both sides, it's not the same number. So that's not a line of symmetry. So we don't really know what the vertex is either. We don't know if it happens before 11 and it's already coming back down, or if it happens after 11. Okay, so that means we're to this place where we have 3 points. Well, we have a lot more than 3. Okay, but we've got this table of values, but we don't have any x-intercepts and we don't have any vertices. So we're going to use the form y equals ax squared plus bx plus c. You know, if you have vertex form, you plug in your h and k right away. If you have intercept form, you plug in your p's and your q's right away. If you have standard form, what's the one thing you could plug in? What can you see right away in standard form? Kenzie? The y-intercept. Now look at your table. Do you have the y-intercept? No, because if we had the y-intercept, we would have a table value for x equals 0. So we don't even know what c is. So the only things we know are x's and y's. So we're going to create a 3-variable system. You can pick any 3 points from your set of data that you want. I usually pick the first 3 because that means they generally have some smaller numbers. But it wouldn't matter. So I'm going to take the first 3 points. Pay attention, my x's and my y's. And I'm going to plug them in. So 2600 is equal to a times 2 squared plus b times 2 plus c. And I'll fix these here in a little bit. 6500 equals a times 5 squared plus b times 5 plus c. And my last one is 8600 equals a times 8 squared plus b times 8 plus c. Okay, really important. You gotta know where those 3 equations came from, right? Because I didn't have the x-intercepts and I didn't have the vertex. I only knew 3 points on my parabola. I pick any 3 points. If Alex chooses to pick 8, 11, and 14 as his 3 points, he's going to be fine. So you can't go wrong with what 3 points you choose. And I plug those in for x and y respectively. In standard form, you have 2 x's, so you have to plug the x in twice. Okay, now, our 3-variable system, let's make it look a little nicer, right? Move this up. Let's fix these squareds, and I'm going to put my coefficients in front of my b's over here. So I have 2600 equals 4a plus 2b plus c. And 6500 equals 25a plus 5b plus c. And 8600 equals 64a plus 8b plus c. And there's my three equations with three variables, a, b, and c. I'm going to have to solve the three variable system like I did in chapter 1. So I'm going to give you some time with your group, see if you can get this solved for me. I'm going to peek around at like which equations you're choosing. Let me ask you this, I guess, before we all get started. To start the three variable system solving, we have to choose a variable to eliminate. What looks like a good variable to eliminate? C. Okay, good. Let's all groups start with eliminating C.
Oh, that makes sense. Wait, who's first?
Yeah.
So we have to keep track of it like we would.
Yes, I would keep track of it. I can't. Some people's work is so messy. I have no idea what you're doing.
Okay.
My brain is gonna explode when I look at it.
Yeah, I'm good at that.
So, which two equations are you guys gonna use to eliminate C?
Multiply a times negative 1 to get rid of c has to be negative.
No, you can just subtract. You can subtract. Wait.
You have to make one more negative.
But you can just subtract instead of that. So you don't have to multiply.
Yeah, you have to multiply.
Okay,
Subtracting is multiplying by negative.
so I'm not.
You're not wrong. I always keep it addition so that I don't like confuse myself. But subtracting all of them is multiplying by the negative.
Okay.
Okay, so most groups using equations 1 and 2. Now, I made 2 negative, so I got all negatives in my answer. Negative 3900 equals negative 21a minus 3b. If you made 1 negative and kept 2 positive, then you would have opposite signs, right, where you should have the same numbers. Okay, so that would be our equation 4.
If I do the same thing, you can make root second quarter. Yeah, so multiply this by. No, you have to eliminate c.
Okay, then I saw most groups just chose, well then let me do equation 2 and 3, right? I'll just go down the row. Did I get my numbers right? It's a 2100, a 39. Okay, Now again, if you switch the signs, like you made 2 negative, not 3, then you would have opposite signs. They'd all be positive, which is totally fine. Okay. Now which variable are we going to eliminate? B. Yeah. In mine, I'll have to multiply one of my 4 or 5s by a negative, so I'll do 5 times the negative. Negative 1800 equals 18a. And so a is negative 100. You can use either equation 4 or 5 to solve for b. So I'll use 5 because it looks like it has some smaller numbers. Negative 2100 equals negative 39 times negative 100 minus 3b. Negative 2100 equals 3900 minus 3b. Let's see, I gotta subtract. So that's gonna get me to negative 6000 equals negative 3b. And b equals 2000. Anybody else getting that?
Yeah.
Okay, got some seconds there. Now, if you have different equations, if your group made different signs, we should still come up with the same a's and b's. So you might have like a small error, sign error, or something that you would want to go back and look for. Okay. And then lastly, of course, we would want to plug into one of our original ones so that we could solve for c. So I'm probably going to do equation 1. So that would be what? 2600 equals 4 times negative 100 plus 2 times 2000 plus c. So that's 2600 equals, this is 4400, so 4400 plus c. Negative 1800. Oh wait, that's a negative 400, isn't it? Oh gosh, that was a big eraser. Sorry. Is this all? Let's see. 2600 equals 4 times negative 100 plus 2 times 2000 plus c. Okay, this is negative 400 plus 4,000, so that should be 3,600. So c equals negative 1,000. Okay, so then our model, now that we have a's, b's, and c's, is y equals negative 100 x squared plus 2,000x minus 1,000. If you're not sure if your model is right, like if you have extra time on a quiz or test and you want to check your model, pick one of your x's from the table and plug it in. So like I think one of our x's was 5. If we plug in 5 for both of these x's and work it out in our calculator, we should get the y value that's in the table, which I think was 6,500. Okay, before I move on, does anybody have any questions there on writing that model? Yes, Jayla.
Why is the 100 and 1,000
That's just the way they solved. So like, I don't know if your 4 and 5 were the same signs as mine. Did you get negatives for all of them?
Oh, yeah.
You did?
Yeah, I just wrote it down.
Oh, okay. Yeah, it's the mathematical solving. So it's like I didn't choose it to be negative, but it does make sense that my a value is negative because then what do you know about this parabola? It opens down. Okay, so think about this. Like if the ticket prices are really low, it's probably because it's not a good show. So maybe like a lot of people aren't gonna buy them, or your price is so low that you don't even make that much profit for how much you have to pay the band, right? But as you start to increase price, there's like a little sweet spot where you've got the price low enough where people will buy it, but high enough that you can pay the band, you can pay the workers, you can do all the things and make a profit. And then there's a price where your price gets way too high that people won't even buy the tickets to come to your show, right? So this is talking about price, and this is talking about profit, and it would make sense that it was a parabola that opened down. Yeah?
So like when you look back at the table in comparison to your model,
Uh-huh.
it's like because it's like going up and then going back down. Will it always be like that?
No, you could have some parabolic models where it has a minimum. The majority of ours are upside down. But like because you see that in the table, like what Mo had described, because you see it going up and coming down, that would also answer Jayla's question. We know A is going to be negative. Now B and C we don't really know, but we know A will be negative if it's going up and coming down.
If you were going to a show with 11 people, wouldn't it make more sense to buy 14 tickets? Or instead of buying 11 tickets?
Well, this is the profit to the people putting on the concert.
Yeah.
So not how much you're paying, but how much, like, the profit would be all the money they take in from ticket sales, but also all the things they have to pay for. Like, with more people, you got to hire more security, and you have to have more workers, you have to have more concessions. So that's also at a cost to you, but at some level, the cost is a good thing, right?
Yeah.
Okay. So, in businesses, you're probably looking for models, and one thing you can do, like with linear programming, which is basically these 3 variable systems, but with a lot of variables, is like figure out where do we put the next scooters, right? We got one on 96. We got one over on Giles. Okay, where's the next scooter's going to be where I can maximize my profit, where it's far enough away, but people live there, so they're going to come, right? We want to know those things in the real world. Okay. Now notice that this asks a follow-up question. What charge should you use to maximize profit? So if you have your model, how would you figure out the charge to maximize profit? Find the vertex. Now, here's the thing that you'll always have to think about. Which part of the vertex do you want? The price, which is the x, or the profit value? You really just want to know the price, right? So once you find your x coordinate on this one, then you have the answer you want. So like this is standard form. I would do h equals the opposite of e over 2 times a. So that's negative 2,000 over negative 200. So cross out my zeros. Was that going to be a $10 ticket? So in that table, the max was actually just before 11. And then 11 was coming back down. Okay, so your homework assignment for tonight is like only 4 problems because the 3 variable systems take longer to solve, but you want to practice going through and that you can actually work out. So 23, 29, 30, and 35. Okay. Jake said last night that online textbook was having some difficulties, so if you're using online textbook to be on the safe side, maybe grab that textbook from your pods and take a quick pick of those 4 problems. Okay. We're going to review tomorrow, we're going to quiz on Wednesday, we'll review on Thursday, and we're testing on Friday. But please don't wait to study Chapter 1 until Thursday. You need to be looking back at transformations, function notations a little bit each night. You'll be happy if you do. Okay. Yes, when were you planning to do that?
I have to check because I have to take a test, but I'm just on Friday.
Okay.
So I'll have to talk to my parents. But if I emailed you,
Yes,
okay.
that would be great.
Yeah, I did actually.
Are they updated?
Yes, okay, I have you Tuesday before. I would get here by like 7:15 or 7:20. It doesn't take the full time. Thank you.
Oh, I did.
Give me 1 second. Jack, are you still coming in during your study hall? Okay. And Hannah, are you coming in during 7th hour?
Yeah.
Okay. That's all I got. Yes, I will take your copy. You have a question, Alex? No, I have my meeting. Alyssa? And Jake, if you want to look at your quiz, I'll need those back. But if you want to read. Okay. Brianna, have you thought about when you might be doing? Yeah, that should work. I usually on Tuesdays go upstairs to DO7. So if I'm not, I put a note on my door, but come here and we can walk up together or. Did you bring your club stuff? Any questions? Yeah, I'm not gonna give you your point back. You gotta be real. Oh, okay. And I would say this, like, interpret what 3 over 1 is. That's 3 is your rise, 1 is your round, so the 3 inches, 1 is started a home. Doesn't that mean a lot more? Obviously, a child. And then it's right because, like, I'm like in my living room, like, I can't read this and I'm tired. So, like, I just want to throw it away. Yeah, it's dry. Wise and X. Because if you put in 90 in the equation, then you yes, right? So I can tell if you use your table, oh, okay. Yeah, you can bring it to me tomorrow. Yeah, I'll take it and then I'll put a note on it and bring it to me. Just bring me the. This is 0.2. Okay. So gullible. That's correct. It's 3 over 1. 15 divided by 5 is 3, and 5 divided by 5 is 1. You got the wrong slope. Wrong slope will give you wrong y-intercept, that's for sure.
Wait, I need to see it.
Okay. What hour do you have time cut? Lunch.
I have a higher projection. This isn't good though, Tom. This is really bad.
Can you stop in tomorrow? Like,
Dude, that's
tomorrow morning,
stupid.
here a little early before class?
Yo, alright.
Were you planning to retake today?
No, it's gonna do it tomorrow.
Okay, yeah. Why don't we stop in tomorrow morning and we'll go over